Okay, hello everyone. My name is Andrei. I'm an engineer and also a maintainer of Hyperledger Iroha, and today I will tell you more in-depth information about features and architecture of our system. So first, I will tell you the main features, which are which we like. First, the command-driven architecture, which allows people not to write smart contracts, but to use existing commands to implement most of the possible use cases, like, for example, asset management or identity management. We also support multiple software platforms such as like Linux, macOS, and Windows. However, Windows support is experimental at the moment, and we are looking for contributors to make this support more stable. We also have Byzantine fault-tolerant consensus algorithm in development. So for the version 1.0, we will have so we will have another algorithm for consensus after 1.0. We also have role-based access control system for permissions, which I will tell you about more in detail later. We have client libraries for also for many popular programming languages and mobile systems. Also, Iroha has it has only a single peer role, which allows people to deploy the system simply, like with only Postgres database as a dependency, and the deployment is also easily done with Docker and Ansible. And another important feature is multi-signature transactions, as mentioned by Sarah, that allows people to like share an account and also perform some more complex operations such as atomic exchange between two accounts. How Iroha is different to other existing platforms. So the regional awareness was composed by looking at Google Trends, and so Hyperledger Iroha is mostly popular in Asia and especially Japan. Like Fabric is more popular in China, and it's probably one of the most popular enterprise blockchain platforms at the moment, and SOTUS is more popular in the United States. So yes, the differentiator from other platforms is that we only have one role, so you don't have like a validator node or just listener node. So each node performs validation and participates in consensus. And we also use SQL state, which potentially allows users to perform some complex data analysis of the blockchain. And as I mentioned, we have a novel consensus algorithm, which is linearly scalable. And it was developed because other consensus algorithm has greater complexity. As for connectivity, we use gRPC, also other popular frameworks. And as for REST, you can use it also with gRPC, but it will require to set up an additional proxy. Yes, as for the business logic layer, right now we don't have smart contracts, and yes, they are in development. But the commands that are implemented should be enough to cover the most popular use cases. And regarding the production and the first major release, Iroha is already used in some production projects. So, well, even though the first major release wasn't done yet. And also comparing to Corda and Ethereum, the main difference, let's say, from Corda is that it doesn't have a Byzantine fault-tolerant consensus, as well as Ethereum, and Corda is not a blockchain because it doesn't store all the history of the transactions, but it stores only the relations between different users. Okay, so moving on to the implementation details, and first the features. Command-driven architecture is about having command query responsibility segregation in our system, so that the transactions are composed of the commands, like the building blocks, and so that people can perform different actions which will be stored in the ledger. So like you see some list of the possible commands, like creating domain, creating assets, and other commands. And as for the queries, they do not change the state of the ledger, and they are used to query the world state view of the current node. And well, since the query is done only for the one node that you select at the moment, well, if you want to get, let's say, an overview of the whole network, you should query each and one of the participants in the network. But if you just trust one single node that you use, you can have only a single query and get the data about accounts or assets only from a single node. Yes, as I mentioned previously, we support different software, like operating systems, as well as different architectures. So you can, well, besides having different operating systems such as Linux and Mac OS, you can also run it on ARM devices, well, such as Raspberry Pi and well, x86. And yes, having having the possibility to run it on ARM devices may allow to use for IoT and supply chain use cases. Yes, we do have Byzantine fault-tolerant consensus in development, which is called yet another consensus, and well, it allows to have faulty participants in the network. So, and well, they will not affect the whole state of the system. Well, also, as I said before, we will have a more, well, an improved version of consensus algorithm after the release, and it will also increase the number of the required participants. So now we require 3 F+1 nodes in the network to tolerate F failures, but but the algorithm that we have in development will require 7 F+1 peers. Role-based access control. This is quite widely used, well, quite widely used system for managing the permissions and what can users do. So that each account has a set of roles, and each role has a set of permissions, and so these permissions define well, what commands can user execute, or what queries can user execute. So, for example, if a user can create roles or create other accounts or create assets, and it is important to define the roles which will be used further in the system in the Genesis block, because we have such a restriction that well, if a user can create other roles, these roles should contain only a subset of permissions that this user has, so that there will be no um, potential like permission elevation problem. And in this case, if you forget to add something, some permission in the genesis block, you might not be able to add it further when you're running the system. We have client libraries for four platforms, which are supported at the moment, like Java, Python, iOS, and JavaScript. Of course, you can also reuse the code that we use in the server side, so you can have a client in C++. And regarding the details of each library, you can check the videos. Probably we will share the slides after the presentation, so the links will be clickable. Okay, so now we can move on to the to the architecture and the pipeline, and I will show you how does the transaction how is it processed in the system. Well, this slide might look quite complex from the first look, but as I will explain it, as I will explain each component, you will see that it's not that complex after all. So first, user sends a transaction to a component which is called Tori, and this is a gRPC server that accepts the messages from the clients, and these messages can be transactions, transaction batches, which are a collection of transactions which can be created by different users, but which should be executed, well, atomically or in the specified order. And it also accepts multi-signature transactions which do not have all the signatures required to execute it. And you can also send queries to this endpoint. And the responsibility of this component is to perform stateless validation of the messages. And what does stateless validation mean is that it doesn't access the ledger or the database that is used in the system. Like, for example, it checks that the account name is valid. For example, it doesn't contain any invalid symbols, or the signatures are valid just from the stateless validation side, that it is possible to verify the signature based on the given public key. After the transaction is validated in Tori, it is sent to MST, which does the further processing of the transaction, and this is the multi-signature processing component of the system. So, for example, if you send a transaction that has all the required signatures, it will just pass further in the pipeline. But if the transaction doesn't have all the signatures, the processor will share this transaction with other nodes, so that, for example, when two people only use some selected participants in the network, so for example, Iroha network is run on 2 nodes, and one node is used in one country, another node is located in another country, and 2 people want to make some atomic exchange, and well, they can only send transaction to the nodes in their countries. And in this case, the MST processor will help them to perform this operation by using the gossip protocol, so that when one node gets a transaction from the user, it will share it to all other nodes, defined by the propagation strategy. And also an important note about the implementation, that the node shares only the transactions which are known not to be present on other nodes, so that no redundant network messages are sent. Moving on, next is the ordering gate, where the transaction is sent after getting all the required signatures and validation. This component has its own cache for the transactions, so that first an ordering gate sends it to the ordering service, and then it waits for the collection of transactions, which are called proposals. And so, well, this is done since there are several nodes in the network, and we want to collect all transactions from all the nodes. And so first they have to send the transactions to ordering service and then get them back in the ordering gate. And since it's possible that some nodes can be faulty, and well, the ordering service may not receive the transaction that a node wanted to send in a given round, this component will first put the transaction that it gets from the MST into cache, and if this transaction is not received in a proposal after some period of time, it will try to send this transaction again to another ordering service. Yes, I think that is it for the ordering gate. And now we can check what the ordering service does. So this is the other end of this interaction for the transactions and proposals. And the ordering service collects the transactions from other nodes into a queue or a set, which is just a collection of unique transactions. And it generates the proposals based on this queue, and well, this queue is flushed by getting the events or getting the rounds events from the consensus. So a new proposal is generated every round. And it also, yes, it also does another validation of transactions, because, well, since we allow faults in the network, it's possible that some node wanted to send invalid transaction to the ordering service. And it also does the stateless validation, and it also checks that transactions were not committed before. After we get a proposal from the ordering service, it is sent through the ordering gate to the verified proposal creator. And this component is responsible for validating transactions based on the world state view. And yes, this is called stateful validation. And so the purpose of this validation is to check whether, for example, when some person wants to do a transfer, that the source account has enough assets for the transfer, that the receiving end also has all the required permissions to receive the transaction. And this is what the component does. And after the transactions from the proposal are validated, they are packed into verified proposal object, which, well, contains stateful valid transactions, and we also notify the client with whether his transaction was invalid. After this verified proposal is created, it is sent to the block creator, and after which it is sent to the consensus. The block creator, well, it simply adds some meta information to the verified proposal, which is, for example, a hash of a previous block and the signature of the node. And after that, it is sent to the block consensus, which well, which collects the votes from the other nodes, and it also votes for the block that the node has created. And after enough votes for the same block are collected in consensus, we move to synchronizer. And well, what does the synchronizer do? After getting the enough signatures in consensus and getting enough votes for them, we move the decision to the synchronizer, which can either append the block which was voted for if it is the same block as the node has created. But if the consensus decided that some another block was committed, then we have to synchronize our node with other nodes. And well, this is done in case we had our node was slow, and for example, we only had the fourth block, but the network has committed 11th block, and we have to download the blocks from other nodes. And in this case, synchronizer will connect to other nodes based on the signatures received from the consensus, and it will download the required blocks and check whether the downloaded chain can be successfully applied to our ledger. And that's basically it. So when we commit a block, we create an event which is sent to ordering service and ordering gate, and this kind of loop goes on and on. So the blocks are created and they're committed to the blockchain. Now we can just do a small recap for the pipeline based on the previous description. Well, I will try to annotate the slide just that we see how does a transaction go through the system. Yes, so first the user sends his transaction to Tori, which performs stateless validation, which is not connected to the database and only checks some like whether the account name is valid and other field validations. Then it is sent to the multi-signature transaction processor, which will share this transaction with other nodes if it is required, and will collect all the required signatures for this transaction. And after all the signatures are collected, we pass this transaction to the ordering gate, which will also cache this transaction for some bad cases, and will send it to the ordering service. So first it goes to the ordering service. And after the ordering service gets it gets an event from synchronizer that some block was committed, it generates a proposal, and so the node will request the proposal from the ordering service, and well, it will send the proposal to the requester node so that the proposal is received. And then this proposal is sent to a verified proposal creator, which performs the stateful validation based on the world state view, and in particular for the SQL database. And after it is validated, we get a subset of transactions which can be committed to the block, and we send this subset of transactions to the block creator. And the block creator will just append some data which is required for the blockchain to exist, like a previous block hash. And this block will be sent to the consensus algorithm. And the consensus will vote for this block, and it will receive all the votes from the other nodes. And when enough votes are collected for some block, this block will be sent to synchronizer. And here we get some decision whether this block is the one that was created in the block creator, and we can append it without any synchronization, or if the message that we got from consensus is different from our block, we will request synchronization, and the synchronizer will ask other nodes for the block that was actually committed in the consensus. And I think that is it. Yes, that is it for the architecture and features. And well, thank you. And please ask any questions if you have.